Hey everybody, I think it is probably about time to start my talk. So just as a heads up, this is a bit of a technical talk. If you want to, if you're the kind of person that really wants to see real technical material, this is going to be that talk for you. This is mostly focused for people who build reconnaissance tooling, or if you found an interest in building reconnaissance tooling. Even if you have a lot of experience doing it before, I guarantee you there's something in this talk for you. Um, but yeah, it's going to be very dense in material. The intent is to share this presentation after my talk. So it'll be up on my Twitter somewhere. But yeah, so if any part of it I went a little too fast or you didn't quite understand it the first time, it'll be up there. You can read it. Even all the things I'm going to be saying are written in the speaker notes, so you can kind of like read the talk back. All right, so anyway, thank you all for coming to Building Faster Than Light Reconnaissance, Guide to Engineering High Performance Recon Automation. Now, if you know me at all, follow me on Twitter or have been to my streams, you'll know that I like Rust. And you may have thought that this talk was basically going to be just me shilling Rust to you, that Rust, let's go memory safety, fearless concurrency, woo. That is not this talk. I will actually only show Rust and the very very end, and it's super brief. You do not need to know Rust, do not need to care about Rust or want to even write Rust for this talk to make sense for you. This is going to be very general software engineering principles. That being said, let's get into it. All right, the year 2021 marks the 30th anniversary of the World Wide Web. Its birth on August 6, 1991 was relatively unceremonious and yet ushered in a new era. What started out as a simple information indexing and retrieval technology has blossomed into an information-based Cambrian explosion. By 2021, nearly 366 million domains were registered under VeriSign alone, who manages the TLD's common net. Additionally, according to the Netcraft survey, 1.2 billion domains likely exist altogether, but the story does not end there. While not a perfect metric, the increasing number of certificate transparency log entries suggests a general upward trend in the density of addressable domains on the internet. Keep in mind that this number is imperfect as it's influenced by the combined effects of the tail end of TLS adoption, domain registration, as well as the average number of subdomains per root domain, which is what we're really interested in seeing here. Regardless, the evidence seems to suggest that the internet is getting even more massive. But that's nothing new, and probably not surprising. The internet is already incomprehensibly enormous, but as a bug hunter, I'm not as concerned with the size of the internet as I am concerned about the organizations I hack on. So how does this affect me? Well, it's no secret that the bug bounty space has been booming. In addition to the number of platforms and bug bounty adjacent businesses that have opened up in the last decade, the number of organizations entrusting the bug bounty community to serve as an important element of their security lifecycle has grown significantly. If you are starting to feel overwhelmed by the sheer amount of assets, targets, and data to collect and hack on, I wouldn't blame you. The size of the internet has grown much faster than anyone could have expected 30 years ago, and the number of organizations participating in bug bounties is growing at a similarly daunting rate. Here to tell you that none of this is slowing down. As bug hunters, if we hope to keep an edge with recon 5 to 10 years from now, we have a pretty obvious question we need to ask. How do we keep up? It's not as simple as waiting for CPUs to get faster or networks to scale up. There are real improvements we can make to our recon tooling today that can drastically improve the rate at which you collect information. And to figure out how we can do that, let's turn to software engineering. It might be obvious that the same principles that allow massive companies like Google or Cloudflare to serve millions and billions of requests each day could be beneficial to scaling up our much more scoped task of gathering recon. Yet, I see loads of scripts leaving heaps of performance on the table because they all approach the problems in the same simplistic ways. And sometimes that's fine. Not every task requires you to be able to scan the entire internet in 5 minutes. But if you're planning on gathering a recon against more than a single asset at a time, it might make sense to shoot for some performance. All right, enough chit chat. Let's first take a look at what our workflow will be in making our tooling faster, and then let's apply some of these ideas in a practical example. There are 4 general principles I want you to think about when you write software: design, implement, optimize, then scale. You first have to decide on an approach based on the available approaches, their trade-offs depending on your high-level goals for this tool or program. You can then take a first pass at implementation. You don't want to worry so much about the fine details of optimizing here, as premature optimization is the root of all evil. You then attempt to optimize your implementation. Keep in mind that by this step, we shouldn't be making massive changes to our program, but sometimes that may be required if we find something particularly egregious. And lastly, though this does include some elements of design, implementation, and optimization, you add the ability to scale out work where necessary and appropriate. This is the least expensive, easiest to debug, and least painful method to writing efficient performance software. So for design, let's say my high-level task is gather subdomains. That's what I'm trying to achieve. This task is general enough that a number of approaches could be selected that are sufficiently different. On the left, we have DNS brute forcing, which tends to be a lower signal per request, lots of I/O, and can provide lots of inconsistent results, though the data is in fact live data. On the right, for much less I/O, a higher signal approach by collecting from passive sources. We make the trade-off of liveliness of the data for far less work. The last bit of complexity here is that with more sources and formats to deal with, the code could go stale rather quickly if a source modifies how data is presented or API limits are imposed. Just another consideration to keep in mind, and engineering is all about considerations. After we've picked an implementation for a software, or after we've picked an approach for a software to use, it's time to implement it. At this step, we should be concerned about high-level decisions about implementation. Your choice of data structures, lower-level APIs, and any algorithmic components will have a factor on how and where we can optimize. These decisions will, a majority of the time, influence the final performance of our software the greatest. Optimization of software is such a deep and diverse field. There's no way one could do it justice in a single talk. I compiled some terms here that refer to techniques, considerations, and strategies for optimizing network-based software, though many of them do apply to just software in general. Keep in mind that a number of these items will require modifying our previous implementation. For example, if we realize after a first pass that concurrency could greatly improve our throughput, some additional work will be needed to be done to support this new optimization. As mentioned before, our greatest source of performance will come from appropriate use of data structures, and when applicable, algorithmic complexity. Though in our specific case of I/O-bound programming, which network programming is, we should also look to batch operations. Occasionally, APIs expose a way for you to batch information up in one request. This is typically very optimized on the implementation side and is preferable to parallelization or concurrency if available. An example batch operation might be inserting multiple rows into a SQL database with a single insert call, or leveraging load data local with MySQL. Otherwise, we'll want to look at introducing concurrency or parallelism into our code. Concurrency is when two or more tasks can run within overlapping time periods, but parallelism is when multiple tasks run at literally the same time. It's a small but important distinction. Typically, these properties are achieved via asynchronous frameworks, like threading, or language features like async I/O in Python, or async await in JavaScript and Rust. Keep in mind that when you introduce concurrency or parallelism to your program, that you'll likely need to synchronize state between threads of execution, though some design decisions can reduce or entirely obviate synchronization requirements. Typical strategies for state synchronization include using a mutex, otherwise known as a lock. However, mutexes can introduce a lot of overhead. It turns out there are strategies for avoiding the use of locks, or heavily reducing their impact, by leveraging atomics, commonly known as lock-free programming. Now, I don't recommend anyone try to write correct lock-free code themselves, but instead use a library that has done it for you in the form of lock-free data structures. Let's say you've done all the previous work in making your code run fast, you've written tight loops, minimized allocations, and algorithmic complexity is low, and it's running highly concurrently as well. If you're doing network-based tasks, you might be pushing hundreds of thousands of packets per second. But what if you want to go even further? Then you might want to look at reducing or eliminating entirely the kernel from your network calls by leveraging technologies such as I/O U-Ring or XDP, both of which are natively supported in Linux. Additionally, both of these technologies support zero-copy modes, which allow you to avoid allocations, which at these speeds start to get expensive. Okay, so after making the fastest code you can without compromising on your readability, stability, or reliability, it's probably time to start scaling out, if you see a need, of course. This will involve modifying our program and workloads to allow multiple systems to take in jobs, perform work on that job, and coalesce a result. While I won't be spending much time talking about methods to scale out software in this talk, some of the key things you'll want to learn about are embarrassingly parallel problems. And yes, that is the official term for this kind of work. It refers to jobs that are trivial to split among individual workers. For example, adding up all the numbers from 1 to 100 is super easy to split up between multiple workers, as we can just add the results up at the end and get the final result. Transactions and ACID are important terms as well, as they relate to the atomic or uninterrupted and ordered reads and writes to a database. You can get some very weird and often impossible to diagnose issues if you fail to use transactions in certain workloads in distributed systems. Lastly, RPCs, or remote procedure calls, as a communication method between machines, is probably one of the easiest ways to get multiple machines to talk to each other, at least at smaller scales with non-dynamically scaling environments. If we want to take things further to support scaling up and down workloads dynamically, we typically want to use a message queue. These are systems that manage a bunch of work and direct it around between services. Services can then pull jobs from message queues to do work on, and then forward a result to where it needs to go. Lots of message queues exist, but some popular ones are SQS, RabbitMQ, or Kafka. Additionally, to support dynamic scaling and easier management of tools, containers and microservice design tend to help and are a well-supported paradigm. Now, I really won't be going into these topics much, but depending on the types of distributed jobs being performed, consensus algorithms such as Raft or Paxos might be helpful. Additionally, concepts like rendezvous hashing allow multiple machines to agree on answers for certain types of problems without communication or synchronization, which can be super helpful property and keeping machines free to do useful work rather than waiting on a steady state in your distributed system. Okay, so I have thrown a bunch of terms at you, and so far we haven't really seen how any of these could apply to our software. I am now going to go through a practical example where we start with a very basic DNS brute forcer, add some basic optimizations, continue to iterate on the design until the DNS brute forcer is very fast and hopefully relatively reliable. Though keep in mind, the purpose of this talk is showing you how to go fast. We will not be discussing so much in depth how we can ensure for this specific task of DNS brute forcing how to be reliable and ensuring that we don't overload resolvers. For that, there are plenty of techniques such as iterating through a list of potential resolvers or even doing iterative resolution yourself. This next section is going to start out relatively easy to understand and might get less so, especially if any of these ideas are new to you or you don't have much programming experience. If you get a little lost by the end of it, that's totally okay. And most software shouldn't need or even want to do the kinds of optimizations I'll be showing near the end anyway. In engineering, everything is about trade-offs. And by the end of this, we'll be paying for our high performance with impacts to our readability, flexibility, utilization, and additional deployment requirements. That being said, my slides will be up after the talk if you want to go through this on your own a little more slowly. Enjoy. Okay, so to make sure everyone's on the same page, let's quickly cover the principles behind DNS brute forcing. Typically, you have a target and perhaps a word list, where the goal is to discover subdomains of the target by iterating through entries in the word list, prepending them to the target, querying the DNS records for the resulting subdomain, and waiting for a response that indicates a valid subdomain. In this diagram, we see that our word list contains sub1, sub2, sub3, and that we're individually querying some recursive DNS resolver for sub1.domain.com through sub3.domain.com. The first and third subdomains return an A record, but sub2.domain.com returns an X domain, indicating a non-existent subdomain. What's great about this diagram is that it actually almost explains how to write the first iteration of our DNS brute forcer. As a heads up, I'm going to be using pseudocode for some of these examples, though many of you may recognize that this pseudocode is quite similar to Python. I'll avoid showing large complex sections of code where possible, but keep in mind that this code is not meant to be copied, pasted, and then ran as is. Okay, with that disclaimer out of the way, let's discuss some of the problems with this code. While I am intending on using pseudocode here, I explicitly want to call out socket.getHost by name as a bad practice for this kind of recon, because I have seen it done in multiple recon scripts in the past. This Python function and its equivalents in other languages may use your system's DNS resolver. This has a couple of problems. It'll hit your computer's DNS cache and host file. This wastes time when we know that neither the cache nor the host file will have our answer. This will then call the DNS configured for your system, which could be the DNS resolver provided by your ISP. Other than this undesirable call, the main issue with this code is that it waits for a response to each DNS query and won't proceed forward until it receives a response. This means we spend a significant majority of our time just waiting for a single packet to hit our system. The first major optimization we can make here is adding in concurrency. Instead of requesting each individual DNS query sequentially, we can send multiple requests and process responses as they come back. Notice how the amount of time we wait around doing nothing drops dramatically. This results in massively increased performance. While many of you may be familiar with the idea of using threads to achieve concurrency, there are actually a number of ways this could be done with different costs and benefits. For example, we could use lightweight Go routines in Golang, async await in Rust, or async in Python. Under the hood, these async frameworks may leverage multi-threading, though this isn't always the case. The core use case of these frameworks is to allow you to create small, easy-to-execute tasks that avoid some of the heavy overhead and OS-level management that comes with threads. That being said, I see a lot of tools using raw threads or thread pools, so let's explore that a bit before we consider an alternative design. Here we see a hypothetical design for our brute forcer that spawns off a number of threads that each do work. In this example, we only show 2 threads, but typically many more spawned. Each thread at initialization is given a slice of the word list to operate on. This is known as work sharing. So if we have 4 threads, each thread will receive 1/4 of the word list. This removes the need for synchronization, which is a plus, but also comes with a downside. If our brute forcer supports retrying DNS queries that were potentially dropped, which is a relatively typical recon scenario due to UDP's connectionless nature, it's possible that a particular thread could become our bottleneck, where an excessive number of retries occurred and is holding up the completion of this job. Ideally, to reduce the weighting on our underperforming threads, we could use a work stealing strategy. Work stealing is a scheduling strategy in which each worker takes a job as soon as it's able to. This way, we don't have a situation where some threads terminate early when they could be doing useful work, while other threads are doomed to run longer due to excessive retries, packet loss, or errors. Here we've implemented a simple work stealing system. We maintain a global word list index that indicates the next entry in the word list that must be processed. When a thread is available to perform work, it grabs a word list entry, increments the word list index, and begins querying for a subdomain. The shared state among threads introduces us to a number of potential concurrency bugs. For example, 2 threads could try and process the same entry before incrementing the index, or the index could increment twice in a row if 2 threads are racing. Typically, a mutex, also known as a lock, can be used here to ensure that threads don't race each other. But it's actually pretty simple to implement this with an atomic integer and a specialized operator called compare and exchange. It's not important to cover the mechanics of atomics here, so we'll move on and address a more annoying issue. With this design, each thread can only have 1 DNS query in flight at a time. That means 2 things. If we want to have a lot of requests in flight, we need to run a lot of threads. More threads equals more requests. A thread spends a majority of its time waiting instead of doing work. Neither of these are desirable. For one, by using threads, we require the operating system to context switch from one thread into this new thread, context switch again to send a packet, switch back into the user land thread, and since we spend most of our time waiting around, we'll context switch back into the next user land thread that has work to do. Instead of threads, I would recommend using whatever async frameworks are available. Typically, these use lightweight userland threads of execution that use much less memory, are much easier to instantiate, and you can usually run many times more of them than threads. Here we just see a design that uses async tasks, such as Go routines in Go or async tasks in Rust. These lighter weight tasks require less memory than threads, are easier to context switch if we're not already pinning our threads, and are usually much easier to create large quantities of them. This means that we can start pushing more packets quickly, but than would be typical with the previous design. However, we run into another issue. With enough async tasks running at a time, we'll start to hit errors when creating UDP sockets to talk to our resolver. This error commonly shows up as too many open files on Linux. Tell me you haven't seen that before. While the solution I see extensively copied around online is increase your file descriptor limit with ulimit, I'm going to tell you that this is the wrong solution. It is a band-aid for a deeper problem. Let me show you. On the left, we see our design thus far. Each packet we're sending, we're creating a socket, sending a packet, waiting for a response, and then reopening a new socket when we want to send another packet. It turns out a lot of recon tools suffer from this problem. Go check your code and your dependencies. If you're using net.dial from Golang in a loop, you might be making this mistake. And I know some of you are. I checked before this talk. Creating sockets is expensive, uses up file descriptors, and we don't actually need to create a new socket if we're talking to a new resolver. Lower level socket APIs typically have support for send to and send message, which both allow you to specify a remote address. On the right, we show a better, less wasteful design centered around a single open UDP socket and send to calls that allow us to specify the remote resolver we wish to talk to. This design will substantially increase the rate at which you can send and receive DNS queries. We can even ensure that each query gets a timeout, and that we can also ensure that every query receives at least one response we deem valid. This high-level design is one that I had built on my Twitch stream a couple of months ago. Leveraging principles from this talk, I was able to send 600,000 DNS queries a second, and if the resolvers, my hardware, and my ISP would allow it, I'd be able to receive a similar number of responses too. Obviously, this diagram is very vague. It's hiding a lot of complexity. So let's look at both of these components in this DNS brute forcer in pseudocode, starting with the socket manager in the center, and then moving back to the query processor on the left. While this is pseudocode and therefore a ton of details like batching of operations and some state machine logic are omitted, the actual socket manager code is quite small. The point is to keep this loop running very quickly. At high speeds, the buffers in your kernel and network interface card can fill up easily, but they can also drain easily. If we ensure a tight loop, we can always make sure the network interface card is fed with packets to send and hopefully ensure there's room to receive packets, minimizing packet loss. When we receive a response, we don't attempt to process it here. We'll immediately forward it to the query processor to determine what to do. Now, again, while the pseudocode here is similarly small, the actual code for the query processor is a fair bit larger. Initially, we try to efficiently wait for a message from the socket or an upcoming query expiration before we proceed in the loop. If a message is returned, we'll either handle the response from the socket or make sure to record the query in the socket manager that was just sent out. After that, we'll move on to query expiration. We have to keep track of query expiration efficiently, so we leverage an augmented version of an algorithm called leaky bucket, which is typically used for rate limiting, but it works pretty well in reverse for demarking items as expired or not. As all of our operations in the socket manager and query manager are batch operations, we're not paying a heavy penalty pushing queries back and forth through async contexts. We're able to approach, but not quite hit, line-level speeds for 64-byte packets on 1 gigabit Ethernet using standard Linux with 0 modifications. So that means no changes to the ulimit, no changes to the network buffers through your kernel, and definitely no special fancy network interface cards. Admittedly, there are some additional performance enhancements I missed in my current implementation, but this is already fast enough to serve my purposes. But what if it wasn't enough? What if we absolutely needed every last drop of speed we could get? Could we go faster? How would this even be possible? Your typical program sending packets looks like this. And the V5 DNS brute forcer we just looked at, the one I had implemented, is no exception. Every time we want to send a single packet, we must make the send to syscall. This gives the packet information to the kernel. the kernel network stack processes the packet, and then eventually the packet makes its way to the network interface card. Eventually, control is returned to the calling context so further packets can be sent or other work be done. This is pretty expensive, making consistent context switches from user land into the kernel just so that we can send packets out or receive them. If you remember from our earlier slides on optimization strategies, one of the first things we should seek out is batch operations. At this point, batch operations start to open up to us in the form of a Linux kernel API called IOU-ring. IOU-ring is an API that allows us to push work onto a ring buffer that is then shared with the kernel. It helps us drastically cut down on syscalls by pushing multiple operations like send, receive, write, read, and any number of them to a ring buffer and then telling the kernel that the data is available for processing. The kernel then takes over, reads data from the ring buffer, and then processes it. Eventually, completion events are pushed onto another ring buffer that you can then read from, but that's not shown here for brevity. Unfortunately, this will require a Linux kernel version of 5.6 or greater to be able to use IOU-ring with sockets. But if we can meet that requirement, then we can easily hit line level. And also, heads up, if you use Ubuntu, you're likely on 5.4, though if you install the hardware extensions kernel, which is pretty easy to do, it's a single apt-get command, you can get kernel 5.8, and this is now an option. But what if that wasn't enough? Can we go even further? We can. By leveraging the same technology that Cloudflare uses to mitigate distributed denial of service attacks, we're able to push out packets at a similarly daunting rate. XDP, also known as Express Data Path, is a technology that allows us to put small programs near the network interface card to bypass the kernel networking stack entirely. AF XDP, a new socket type added back in 2018 in the 4.18 or 4.20 Linux kernel, allows us to send and receive packets from userland without the need to install custom drivers. Let me say that again. This technology is in the same Linux you're using right now, and XDP is likely supported on the networking interface card in your personal computer. But drivers for higher-end data center tier network interface cards like iXGBE or i40E have specialized support that enables zero-copy mode, further reducing your allocations. Okay, so how fast is AFXDP? I've clearly hyped it up. There's a lot of data being read and sent about here. Like, there's got to be a bit of overhead, right? It's line-level speed for a 10 gigabit Ethernet card and can go faster. In fact, AFXDP can peak around 22 million packets per second send and receive for 40 gigabit Ethernet cards. This is all well and good, but both IOU-ring and XDP appear complicated to use. Sending packets today is simple with a singular send-to call or already implemented abstractions over APIs like ePOL. Is it even possible to make these technologies easy to use? Is there even a use case for it? Back in 2019, I started a project called Resync. It's designed to be a super scalable, incredibly fast, and very reliable recon platform with a simple mission. I wanted to curate, monitor, and catalog the world's attack surface. The world is a big place, so to make that happen, I had to invest in making Resync fast. I recently created an API I called the Cherenkov Dataplane that allows both threads and async tasks to leverage, with zero work, any of the carefully tuned send to, IOU-ring, or XDP's APIs within. Testing on my home machine, I was able to hit line-level packet sending speeds with only 8% CPU usage. So that's 8% CPU usage for 1.4 to 1.5 million packets per second. I actually bought a 10 gigabit Ethernet card before this talk, but unfortunately I didn't have any other 10 gigabit networking equipment lying around that I could get some stats on. Though admittedly, I probably could have tried this on bare metal and AWS for a few minutes. That being said, using technologies like XDP for your day-to-day recon is honestly pretty insane. Even on most VPSs, you wouldn't have access to network interfaces that support XDP, even in XDP generic mode, since a majority of these are virtualized drivers. And most low-tier VPSs max out near 200 kilopackets per second anyway, which can be easily reached with other methods and careful tuning. If you enjoyed this talk, found it interesting, or want to learn more about resync, I highly suggest you follow me, SecurityBee, and the resync Twitter account at the addresses below. Also, go check out resync.gg. We just launched our site last night. Would love for you to check it out. Thank you.